Okay, so picture this. You're climbing out after takeoff, full power dialed in, but your aircraft, maybe your trusty Cessna, it just feels sluggish. It isn't performing like you'd expect.
Mhm.
Or maybe you're on an IFR approach, expecting the haze to clear as you descend, but it just hangs there really stubbornly, even on what seems like a clear morning.
Right.
It feels like there's something invisible pushing back, you know? Have you felt that? Is there some kind of unseen force we GA pilots really need to get our heads around?
Oh, absolutely. That feeling, what you're describing there, that's a classic, pretty much textbook, of a temperature inversion.
Ah, okay.
Inversion,
Finish?
and you're spot on. For us flying BIR, or
Mm.
really anyone in a lighter aircraft, it is an invisible force. It's this atmospheric thing that can seriously complicate your flight.
Right.
So our mission for this deep dive is to really unpack these inversions, what they are, how they form, and crucially, why understanding them is, well, it's not just exam fodder. It's vital for safety, a silent threat sometimes.
Okay, let's dive in. What exactly is a temperature inversion then?
So basically, it's the atmosphere doing things backwards. Normally, right, you climb, it gets colder, standard lapse rate.
Yeah.
But with an inversion, that flips.
Mm.
You get a layer of warmer air sitting on top of a layer of colder air near the surface.
Warmer above colder. That seems wrong.
It's counterintuitive, exactly. The atmosphere's normal temperature profile gets turned upside down near the ground.
So it's like this invisible trap. How does that actually happen? How does it form in the real world? Is it just a nighttime thing?
Well, the most common way, the one you'll likely encounter most often, especially preparing for an early flight, is called a radiation inversion.
Radiation inversion. Okay.
Yeah, think about a clear, calm night. The ground loses heat really fast,
Mm-hmm.
radiates it out into space.
Mm-hmm.
This cools the air right next to the ground. So you get this layer of cold, dense air forming at the surface. And if there's not much wind to mix things up,
It just sits there.
exactly, it just settles, trapped underneath the warmer air that hasn't cooled down as much higher up. It creates this incredibly stable layer, almost like putting a lid on things down low.
Ah, okay. So that stable air is key.
Very key. While there are other ways, like fronts, that morning radiation inversion is definitely the one for GA pilots to keep a close eye on.
Right. Makes sense. So we know what it is, how it forms.
Hmm.
But, the practical side, why does this really matter to me sitting in the cockpit flying IFR?
Okay, yeah, this is where it gets really interesting and directly impacts your flying. Let's break it down.
Please.
First off, reduced visibility. Because that stable, cold air is trapped. Like we said, it holds onto everything. Pollutants, moisture, dust, smoke.
Like a container.
Precisely. So what this means in the cockpit, expect significantly reduced visibility below the inversion layer.
Yeah.
Haze, fog, smog. It can linger persistently.
So even if it's clear above.
Exactly. Your pre-flight might show clear skies, but if there's an inversion forecast, you need to anticipate that landing or transition to visual could feel much more like you're right down at IFR minimums.
That's a huge point. So it's not just annoying haze, it directly impacts seeing the runway environment. Are there specific IFR scenarios where this gets particularly tricky?
Definitely. That transition from instrument conditions to visual conditions on approach. You might break out technically, but still be in that really murky layer. It's a recipe for potential disorientation or needing a sudden go-around.
Okay, visibility. Got it. What else?
Next big one. Aircraft performance degradation. Now this one to feel backwards.
How so?
That colder air at the surface is denser, which you'd think helps performance.
Right, I'd expect a better climb.
But the extreme stability of that cold, trapped air mass resists vertical movement. So here's a key bit for what examiners expect versus what actually matters in flight. Even with full power, you should anticipate a noticeable reduction in your climb rate when climbing through that cold layer.
Really? Even with colder, denser air?
Yes, the aircraft just feels sluggish, like it's fighting to climb out of that stable pool of air. It might even feel like you need a longer takeoff run. The big takeaway, don't chase airspeed if it feels sluggish on climb out. Focus on maintaining the correct pitch attitude for a safe climb.
Wow. Okay, so full power might feel like half power because of the stability, not just density altitude. That's crucial.
It really is. And finally, the inversion's sort of hidden danger, wind shear.
Ah, where the layers meet.
Exactly. At that boundary, the inversion layer, where the cold, stagnant surface air meets the potentially different, maybe faster-moving, warmer air above, you can get significant changes in wind direction or speed.
Okay.
So, how to remember this for the test in the skies. Be prepared for sudden, unexpected changes in airspeed or vertical speed, especially right after takeoff or during the final approach phase. It's not just bumps. It can be a sharp, sudden shift, low-altitude critical phases. You need to be ready to react.
Visibility, performance, wind shear. Okay, that paints a clear picture. So, knowing all this, how can we, as GA pilots flying under BIR rules, best, anticipate this or manage it?
Awareness is your absolute best defense. And that starts, as always, with a thorough pre-flight weather briefing.
Looking beyond just ceiling and Vs.
Way beyond.
Huh.
Look specifically for temperature profiles, check sounding data, SQT logs if you can get them, or even just METARs and TAFs showing a big temperature difference between the surface and slightly higher up, especially after a clear, calm night.
So, spotting the signs in the forecast.
Yes. If you see signs pointing to an inversion clear night, low wind, morning mist forecast, then plan for it. Expect lower visibility for longer, anticipate reduced climb performance, be mentally prepared for potential shear. Build in extra margins.
That's really practical advice. It really underscores that understanding the why behind the weather isn't just academic for the BIR exams. It's about flying smarter and safer out there.
Absolutely. And, this raises an important question for you to think about.
Right.
Next time you're prepping for an IFR cross-country, looking at that weather data, how much more closely are you going to look at those temperature details now? Recognizing they might just hold the key to whether your flight is smooth or significantly more challenging.